Hello everyone, welcome back to Calculus. This time we are going to study section 3.6, chain rule. I do consider chain rule it is one of the most important rules in Calculus 1. And also, I don't want to scare you, it might be one of the most difficult topic to understand. So let's give a try to see if we can have a clear idea how the chain rule works. Before we start, let's still review quickly some older rules and formulas we covered. And it's all about derivatives. So sum and the difference rule, I suppose we know this rule very well, right? And also there's a rule called as constant multiple rule. Constant multiple rule. The derivative of constant times function, it is constant times derivative. And then more importantly, you want to know the product rule and the quotient rule. I think we explained before. I really try to present product rule and the quotient rule together. Clearly, this pair of u and v represents a product. So the derivative of a product is u prime v plus uv prime. That's a product rule. And also, as I'm saying, you may want to try to see if you can get a quotient rule together. Okay, quotient rule in a similar fashion. Certainly, we need to have quotient u over v. The derivative quotient u prime v, uv prime in the same order. For the quotient, you take the difference. And also for the quotient, there must be denominator. It is the original denominator squared, v squared as denominator. So these are the rules, and I say these rules just help manipulate the derivative, the way to generate a derivative. It may not provide the derivative directly. And then these rules, actually I consider those following the other formulas. They give derivative directly. Okay, they give derivative directly. Hopefully you still remember this very well, the power rule. The power rule, okay, the derivative of a power function. Okay, you bring down this power of r as a coefficient, at the same time decrease the power by 1. I explain the other side just in a moment. And then we also learned the derivative of the exponential function. It is the only function such that the derivative is itself. Okay, dx of e to the x, it is e to the x itself. And also we got some trigonometric functions, right? I don't want to go through all the details for reviewing purpose. I want you to remember at least those 3 rules: derivative sine, cosine, and the tangent. And do keep a tangent in mind too. Even though I guess in my class I would not, well, mostly we will not deal with tangent a lot. But anyway, I think it's just good to know the derivative tangent, derivative tangent. Those are the formulas. They do give derivatives directly. And also to the right column, you see, really I'm saying these are the same formulas. I'm just doing a different notation, okay? In this part, to the left column, x to the power of r, it is a function, power function of variable x. So d dx, x to the power of r, it makes sense. And then to the right column, I'm saying, well, we could have different names for functions, and we could have different variables for the function. So this time, I'm saying I'm having power function of u in terms of, well, the power function in terms of u. So accordingly, if you use the prime notation, that still will work. But anyway, I say this long notation, okay? It makes more sense because it indicates clearly we are having a power function in terms of u. So accordingly, the derivative, it is written as d du. And you look through this thing carefully. I'm saying those two, the left one and the right one, the same. And then if you agree with me, hopefully you have no problem to see these two, they are the same, or they are equivalent, or really they are the same, not only equivalent, they are really the same, just with different notations, And the same for the following formulas. The left one and the right one, they are the same. I just use different notation. And still for quick reviewing purpose, I'm having some very simple examples. Derivative x to the power 10, and that is 10 to the times x to the power 9 according to the power rule. Or maybe in case if we have a function u to the power 10, you want to write this du, okay, because there's no place for x at all. So it is derivative of this power function with respect to u. It turns out to be 10 to the u, 10 times u to the 9. I suppose you do understand that really these are equivalent functions. X to the 10, u to the 10, they are just the equivalent. Or really they are the same power function precisely. Okay, then derivative sine u, well actually it's the formula, it is cosine u. I just want to say we could, it's very common we talk about the sine x, cosine x, or we also could say sine u, sine t, sine r, sine s with any variables, okay. And later, the next one, I just change this u to t. Okay, derivative of cosine t, then we write d dt. If you have variable r, then it would be d dr. I'm saying this is notation, the dd notation, it is longer and it takes more space. And, but anyway, it makes more sense. It tells two things clearly, the function we are having and the variable we are talking about. DD notation. DD notation, it is better because it indicates clearly the function and the variable. And also, indeed, well, remember this section we are talking about the chain rule. We haven't got chain rule started. So if you really understand, if you insist to use DD notation, it will help to understand how chain rule works. Okay. So let's take a quick look at my first example. Let's consider the derivative of the function y equals sine of x cubed. And also to be clear, maybe I can type a little more here. This function, just make sure you do understand it clearly. Maybe it should be considered as parentheses inside the sine, okay, x to the power 3. Yeah, it's the same function like this. And we do understand the derivative of sine x, that's cosine x, right? And then I guess I don't want to say derivative of sine x cubed, that's cosine x cubed. Even though it might be a reasonable thing to expect according to the rules so far we learned, but really it is not true. It is not true. So what I did, okay, by the way, again, speaking of those rules, you can write those rules in different notations, but anyway, you are going to write the entire rule in a consistent fashion. You cannot have anywhere with you have u and x or some other variables mixed, okay. It will have to be x only or u only. So this time, what I did here is I created something, a new notation, u to represent x cubed. I think it's very common in mathematics. When we have a quantity or expression maybe a little too big or hard to handle, and one way to treat the bigger part or the notation, the bigger expression is to represent it with a single notation. So u as x cubed. And the thing is, you want to understand, when I take u as x cubed, the function y in terms of u, it can be written in a very simple fashion, right? This is a very basic sign. Y is sine u. Okay. In terms of u, y is sine u, no more power of 3 anymore. Okay. And then I want you to realize there are two things. Okay. For y equals sine u, we can calculate the derivative. This is the point, as I said earlier, you want to use dd notation at a single prime. It's maybe you want to say, okay, I got it. I can use y prime to denote the derivative. But anyway, derivative, the prime notation, it's easy to write. But anyway, sometimes it's just confusing. Okay, so from here, the derivative we calculate, it is the derivative in terms of u. So it is dy du. So it's a cosine u. And clearly, you see the writing dy du, it is not the same as dy dx, right? So which means we are all good. We are not done yet. We are not done yet. Dy du is just part of it. Okay. At the same time, we know u, it is a temporary notation I created. U is a function of x, right? So I can calculate a derivative u. Or still, I say if you want to use u prime is fine. But anyway, you'd better write it out clearly. The derivative we are having for u here, it is du dx. Derivative of function u with respect to x, that's a 3x squared. We got two derivatives, dy du and du dx. And we got two derivatives, but anyway, neither of them it is the derivative we want. We want to have dy dx. But anyway, we are really close. So watch closely. I'm saying dy dx, it is arranged as the product of those two derivatives, right? Dy du times du dx. Keep in mind, really, those are the dy du. It's a derivative notation. Itself, it is not separable. Same for du dx, it's not separable. But anyway, the way to help understand how chain rule works, at least in the beginning, you may want to consider, well, you use dd notation all the time for for the derivative, then dy du dx. Somewhat you can think to yourself. Somewhat like a du is cancelled. Okay, that makes sense. We do have dy dx left. Indeed, it is just true. And indeed, I'm saying this is exactly the chain rule, the formula for the chain rule. The chain rule has a formula. That's it. This is the chain rule formula. And then take a look. What is the actual result we may expect? Dy du, it is cosine u. Du dx is 3x squared. So I honestly just copy and paste them together. That is the product of those two derivatives. But anyway, you want to think it very carefully. We are given a function in terms of x, so to calculate derivative, I would say we do expect the answer back in terms of x only, right? Not u and x mixed. So I just realized I could get this u back to x because u related x cubed. So in the end, this is the answer I provided. Cosine u, it is cosine x cubed. And this 3x squared, you could still keep in the end. But anyway, I guess if you keep this term in the end, you are going to have a parenthesis there. And make sure you let people know this is not a part of cosine. So what I did, I simply moved the 3x squared to before cosine. So clearly cosine, it is not applied to this 3x squared. And then surprisingly, this is exactly what I got. Dy dx is 3x squared times cosine x cubed. It is for the derivative of y equals sine x cubed, or in the equivalent form, you can have this pair of parentheses. And indeed, this is the beginning of the chain rule. So how about you take a break to take a close look to see if you really understand the idea. Also, I'm going to take a break, and thank you for watching. See you next time.